Thank you. Sounds like exciting times at the University of Illinois. I wish I could say the same for the University of Tennessee right now. So are we okay? We're coming on here. Yeah, that was certainly very interesting to hear. As my kids were growing, I got a kid in here somewhere. I did. Where'd he get? He disappeared. Oh, there he is over here. I was always telling them that you know they were interested in science and math and stuff, and they wanted to be engineers. And you probably don't remember this, but I said the future is at this interface between the physical sciences and the biological sciences. So make sure while you're in high school that you take all that good bio stuff in addition to the physics, math, and chemistry. And I don't think they listen to me, but now at least he's working a little bit at the biological interface. My older son is a postdoc here right now. So what I'm going to do is say that I know nothing about biology. I hated biology when I was in high school. I stayed away from it like the plague. I regret that. I have not had time to learn enough biology to where I can interface it well with what I do. And I'm using that as an excuse then to basically say that in my talk today, you're not going to hear a whole lot about biology. It's mostly going to be about indentation and engineering and math and mechanical engineering and physics. It's not going to be a whole lot about biology, but hopefully some of these things will apply over into the biological areas. I will also say that I am trained classically as a metallurgist. And so for me, the number one materials are metals, and they're, of course, at the other extreme from soft materials. I moved out of metals a few years ago into ceramics, which are even further away from the biological materials in terms of mechanical properties. You know, please excuse me if I misspeak as I'm talking about some of the softer materials. Softer materials for me are polymers, but I heard someone laugh at me today when I said that a polymer was a soft material. So what I'm going to do today is talk about nanoindentation and talk about how we can probe mechanical properties with nanoindentation. Of course, with the key being that we can do this at extremely small scales, and that then is what seems to be applying then in the nanobio world. This talk is in its completion is it's a whole half-day course in nanoindentation, and obviously we're not going to do all of that in 30 minutes here today. So I'm just going to get started on this stuff. As we go through here, you'll see that there's a lot of things that go on in this nanoindentation world, measuring properties that you might be interested in. If you want to know more about some of the things that I don't talk about today, please catch me at coffee, and I'd be happy to share this with you. I've got a lot of stuff in this talk. There's 100 slides in this talk. Okay, so this is the natural starting place, which is the nanoindenter that we use. And it's a very simple device. It's a device that simply applies forces, very small forces, in very controlled ways. And we do that in our machines via coil and magnet assembly. This is basically a speaker coil. So by flowing current through the coil, the electromagnetic field interacts in a way that by controlling the current, we can simply control the force that we're applying to a device down here. The device down here is, in fact, it is a diamond indenter. And that indenter then is pushed into a specimen. And what makes this different from sort of normal hardness testing is that as we're pushing it in and withdrawing it from the specimen, we measure the displacements of the device so that we can get force displacement curves as we're pushing the indenter in. Now, and also withdrawing. The basic idea here is that force displacement curve can be measured down in the nanonewton range, and the displacements can be measured down in the angstrom range with some of these devices now. And so you can get force and displacement information, and the idea is that there is a whole lot of stuff in that curve that can be measured from nanometer and micron size contacts that tells you things about the mechanical properties of the material. And then you have the ability then to go in and measure some of those things and probe those things without actually having to look at indents. So you do it from force displacement curves. Now, in recent years, there's been some variations on that technique, and I'll probably talk some more about these. I've got another talk tomorrow. We'll talk about these, where instead of using this thing as an indenter, you use it just as a small compression tester. And via things like focused ion beam milling techniques, we can now go in and we can make small specimens like that. That one's a few microns across. You can make these things hundreds of nanometers across. And you can use this as a compression testing system to measure force and displacement as you would in a macro scale test on a compression specimen to get force displacement data, again, down at the micron in the nanoscale. Now, as I go through today, I know as a physical scientist who's interested in hard materials, I need to say this, that my specimen that I'm going to be talking about with respect to indentation is presumed to be flat and smooth, okay? That is a presumption in almost everything that I'm going to talk about here today. I know in the bio world, things are not flat and smooth, and that presents some challenges. And also, I would point out that you don't have to test flat things. You could test water balloons if you want to and learn things about the properties of the water balloons if you want. The whole idea behind this instrument is it measures forces and displacements down at the scale that you need to probe the mechanical behavior of what's going on in your specimen. But as I go through, specimen is flat and specimen is smooth, okay? All right, now, from that, we get load displacement curves, and so this is a load displacement curve from a calibration material, fused silica. We load up, and as we're loading up the indenter, and by the way, this indenter is this triangular pyramid called a Berkovich indenter. That's the primary indenter that we like to use. These things are made out of diamond, can be ground very sharp by the guys that used to make jewels for watches in Switzerland. They don't make jeweled watches over there unless you're buying super high-end Rolexes anymore. So they're making nano indenters instead, making lots of money doing it. As you push that indenter in, that is a sharp, geometrically similar, self-similar object. As you're pushing it in, you are elastically and plastically deforming the material, so you're making the permanent hardness impression. As you unload, in this material, you're recovering the elastic portion of the deformation. You know that's elastic because if you reload and unload, and that's done 4 times in this one, then this is perfectly repeating itself. It's perfectly reversible deformation or elastic deformation. And the point is that by having a loading curve and an unloading curve, you then have some information about elasticity and plasticity. There's basically 2 equations there, a couple of unknowns, and so you can use the data that's in that curve, in those curves, to extract basic information about elastic and plastic properties of the material. And so the idea then, this is actually a fairly big nano indentation. It's made to 1,000 nanometers. We can do this same thing easily at 100 nanometers, and with a little bit, well, actually with a lot of trouble, you can do these things down at the 10 nanometer scale, but you have to be extremely careful when you get down there. I'm often asked, what's the smallest nano indentation that you're comfortable making and taking property measurements out of with? And the answer is that in my systems, the ones that I work with, about 50 nanometers. I don't really want to work below 50 nanometers. Life gets too messy. Lots of issues there, so we don't need to talk about that. All right, now, again, starting from the presumption that you got a flat surface and you're going to be pushing into that surface with an indenter, the one thing that you want good control over is what the geometry of the indenter is. And there are a lot of different geometries that you can use. The one that we like to use is this Berkovich. We like this one a lot, the Berkovich indenter. It's a triangular pyramid. The reason we like that one is that a 3-sided pyramid naturally terminates at a point, and so you can maintain geometric self-similarity to very small depths. That is very different from what happens with the Vickers indenter, which is this classic thing used in microhardness testing. That's a 4-sided pyramid, and unless you're very lucky, a Vickers pyramid does not terminate at a point, it terminates at a chisel edge. It's like the roof line on a house. And what happens then is that as you go to smaller scales, you start off at big scales and things look geometrically self-similar, and then as you go to smaller scales, the geometry transitions from being pyramid-like to being chisel-like. And you don't want that to happen. You want to maintain the geometric similarity, and that's why we like that indenter. Cones, in principle, are really really important indenters to have. Because a lot of the modeling that we do is done with conical indenters because the axisymmetric nature of them makes them simpler. The problem with a cone is you can't get the diamond guys to grind you one that is geometrically very, very perfect. You can see that this one, there's some fourfold symmetry to that contact. That's because it's ground out of a 100 diamond, and the grinding itself is not is anisotropic. You can also see that the tip's not very well defined. And the reason the tip's not very well defined is when you get down to about the micron scale, these guys don't have control over the grinding processes anymore. And so when you get them to make a cone for you, they'll always say, well, what radius tip you want on there? And so I say, I want the sharpest thing you can make. He says, what radius tip you want on there? You're not listening to me. And I say, I want it as sharp as you can get it. He says, if I don't put a radius on the tip of this thing and you look at it in a microscope, it's going to look like the Matterhorn, okay? So it's messy when it gets down there, so they like to put these small radii on them. So you can't get a cone. You simply can't get a cone. That's actually a good challenge. There are some new techniques that could conceivably be used to do that. Cube corner indenter is a sharp one. It's like this one, but it's more sharp. That is one that's nice because it induces a lot more plasticity in the material. It also causes brittle materials to crack. Hey there, buddy, how are you? Long time no see. So we like that one for that reason. Spherical indenters are very important, and I suspect in the bio world there's probably a lot of interest in using spheres because the spherical geometry is nice from a contact mechanics perspective. One of the nice things for spherical indenters in my world, in the hard materials world, is that because they are not singular, they're not pointy, then as you start to push this into the material, the stresses are finite to begin with, start at 0, and they build up as you push it in. And so you start off in the elastic regime in the material, and only later as you push this thing in further and further and further do you get to the plasticity. So you can actually use that to probe the transition from elasticity to plasticity. One of the problems with spheres is it's very hard to get small spheres very geometrically perfect. The smallest spheres that we have ground to about a micron or so, or that we have ground are about a micron or so in size. You get down less than that, and the diamond guys just don't want to mess with you too much anymore. So another challenge there is to come up with techniques for making small spherical indenters out of materials that are both stiff and resistant to plastic deformation. Okay, again, I'm working on flat surfaces, right? You guys want to work on water balloons and things like that. Okay, I know people don't like that term water balloon, but internally stiffen the water balloon or whatever it is. Okay, so where are the applications for this stuff? Well, they're in the old days. The first applications for nanoindentation, which were in the early 90s, were in the microelectronics, the thin films industries, where you want to be able to measure the properties of very thin films on substrates, this being aluminum, silicon. These are indentations that we did back in the late 80s. So these are very old ones, but the first nanoindenters that were sold really helped the microelectronics industry start to understand what the properties of the films were that they were laying down. Well, you might say, I know what the properties of aluminum are. Well, you may know what the elastic modulus of aluminum is, but you don't know what the hardness is because hardness depends on the way that the material is processed, and they were very interested in knowing what the hardness of these films were as well. And so this was really where nanoindentation took off. Other applications, composite materials, obviously flat material here. This is one that we made. It's a chromium silicide lamellar eutectic alloy. There are two phases in here. This was indented with Berkovich indenter, and you can see that some of these indents are real small and some of these indents are real big. And these are lamellae in this thing that have lamellar spacing of about 10 microns. And basically the difference here is that this chromium silicide phase is extremely hard. And so that's this phase, which has very small indentations, all made to the same load. And this is then the softer phase, which is the chromium phase. Chromium is actually a pretty hard metal, but it's softer than the chromium silicide, and so you start to get bigger indentations. And you can use this tool then to probe and map the hardness along a surface with sort of micron resolution. There are a lot of applications in bone, and I'm not an expert in this, but we've dabbled in this a bit. I actually got started in this in an interesting way, and I think we were probably among the first people to do some of this work. That happened because I was approached by, I was in Tennessee, in the eastern part of Tennessee. In the western part of Tennessee is the University of Memphis, which has a very good bioengineering department. And there was a very nice, very good faculty member there at the time by the name of Jay Rowe, who was a bone guy. And Jay came over and said, hey, I think this technique that you've got would be really interesting to start looking at some of the mechanical behavior of bone, some of the microstructural features of bone. And so we started a collaboration back in the mid-90s that was very fruitful and led to a lot of work in bone, in this particular case showing that the modulus of the bone is in fact a function of the angle from the transverse plane, that this material is very anisotropic, even as measured in nanoindentation, that the elastic modulus is quite anisotropic. Tragically, Jay Rowe, at the age of 39, died of a heart attack on New Year's Eve in 2001, I think, and that was sort of it was a great loss to the community, because that guy was really bright. Other applications, I put this one in because this is kind of, that's a biomaterial, right? That's a soft biomaterial. That part soft biomaterial. The reason that I put this one in is that this is actually what the very first commercial nanoindenter was sold for that application. It was sold to probe the properties of ion-implanted layers that are put onto hip joints to harden the surface. And this is another good example of the kinds of things that can be done. The ion-implanted layers are only a micron thick or so, and no one had any idea how much that was really hardening that surface. And so nanoindentation, being able to do this at 100 nanometers or 10 nanometers or so, the first commercial nanoindenter was sold to a company that was interested in trying to determine what the hardness of the surface layer was on that hip joint. Now, so this thing gets into sort of the Nano 101 course. So that, in a nutshell, there's the 4 hours of this course, which we're not going to do. I like to point out that there are a whole lot of things that you can do with nanoindentation, and so, you know, the sky's the limit, and I don't have many bio things listed up here, so you could add the bios on if you wanted to. We probably ought to do that. The instrument itself can be used in several different modes when testing hard materials. This talk is mostly about indentation, where we're using this thing as an indenter. But you can also use this thing for scratch testing. So scratch testing, if you've got a film or a hard surface or something or other, and you want to determine if it's resistant to scratching, you bring the indenter down on the surface, and then you drag the surface laterally. And you can, in some instruments are set up to where they're instrumented not only to measure the vertical forces and displacements, but also the lateral forces and displacements. And that tells you lots of things about what's going on during the scratch testing. Fiber pushing, this is something in the composite materials design. I don't have a picture here. I got one the other day. I forgot to put it on here. This idea is you cross-section a fiber strengthened material, and if you make these things in special ways, you can go in on the fibers and you can push on the fibers, and if you're lucky, you can make that fiber start to move in the matrix. And when it moves in the matrix, it's starting to tell you things about things like what is the friction between the fiber and the surrounding material, those kinds of things, and those become extremely important to designers, where in composite design, it's mostly about what are the properties of that interface and how is energy dissipated at that interface. MEMS testing, that is a mirror that's used for switching phone calls. It's gimbaled in a couple of directions, so you can go in and use these devices simply to measure forces and displacements on all these MEMS devices, calibrate them. And then over the last 10 years, this micro pillar testing stuff where you go in and you make small pillars with focused ion beams and things of that nature. You find out that there's a very interesting world of material science when you start to make specimens that are just microns or submicron in dimension. Lots of interesting things happen there because as a material scientist, I'm always taught that pure materials are not or perfect materials are not the interesting ones. It's the ones with defects that are interesting. Defects are not necessarily bad actors. They can help you do things. And if you get these specimens small enough, you can get down in the world where there are no defects or there's only one defect, and you can start probing those things that we're all taught in the classroom about what it is that's controlling strength in materials. Okay, so what I'm going to do in the remaining time, and I need to quit it by 9:15. Do we want, wait, 5 minutes of questions? Is that what we want? Something like that? Yeah, okay. I'll talk about the measurement of hardness and elastic modulus, because those are the things that we really do well with nanoindentation. But there's a whole other host of things that you can do. This crowd is probably going to be interested in measuring storage and loss modulus. So these are viscoelastic properties. And I probably won't get to that today, but I may, if I don't, I'll talk about it tomorrow afternoon a little bit, how we do those kinds of things. Yield stress and work hardening, you can measure those things as well. And we're going down in sort of the order of what we do well to what we don't do well, okay? So we do the things on the top well. We do that reasonably well. We do this okay, but not great. Fracture toughness, we're still working on. There's some things you can do there. Michelle knows some things about that. Creep, it's getting really difficult. And actually, I need to move residual stress up the list because we're getting better. We're getting better on the residual stress things. But these are all properties of the material, mechanical properties of the material that you can measure with this thing in the indentation mode with some simple principles of physics. So let me talk about hardness and modulus. In order to do that, you have to have a model for what's going on because you're going to take this load displacement data and you want to back out what's happening. The model that we use is actually one for elastic deformation of a half space. It's intended to model what happens in the unloading curve being the one that's primarily elastic, at least in an elastic plastic material. If you're in a viscoelastic material, you can't do this anymore, by the way. So beware. If it's viscoelastic, as a lot of biological materials are, then you have to do other things. But if it's just elastic plastic, then there's this model from Snedden that tells us everything we want to know about forces and displacements for any shape of an indenter as long as the thing is axisymmetric. Now that's a big mess, but one of the things that we showed early on is that all this mess up here can be simplified to a very simple relationship that looks like this. This says simply that the stiffness of the material in contact, which is the force, which is the slope of the force-displacement relationship. So we're measuring forces and we're measuring displacements. We can measure that slope with a lot of accuracy, that's equal to 2 times the effective modulus squared, the effective modulus. The effective modulus is a combination of the modulus of the material and the modulus of the indenter, at times the radius of contact, which then translates to an equation that looks like that in terms of the area of contact. And so this equation, stiffness equals 2 over square root of pi, E effective times the square root of A, becomes the basic equation that we use to analyze a whole lot of stuff that's going on in nanoindentation. And the idea is simply this, that S is measurable from the force displacement curve. And if we can measure S from the force displacement curve, then if we know the modulus, then we can get the contact area, and that gives us something about the hardness. Yeah, we'll get to that in the next slide. Or if we know the contact area, then we can use that to measure what the modulus is, okay? So that is sort of the fundamental equation of nanoindentation. So the question that was asked is, how do we get these two things separately? And that requires a slight leap of faith, and a lot of people don't appreciate this, but there is a slight leap of faith. It is based on the idea that the Snedden model is correct, but the Snedden model is based only on elastic deformation. The plasticity is not built in there, and there are complications that are as a result of that. But if you believe the Snedden model, then the basic way that you get those parameters is through this series of equations. That the contact depth can be determined from 3 measured parameters. Those are the maximum depth of penetration, the maximum load of penetration, and the measured stiffness, the measured unloading stiffness. Those are all measurable quantities. That the contact depth is given by those three parameters, a geometric constant, which we think is close to 0.75 for reasons that we can talk about later. And that gives us the depth along which contact is made between the indenter and the specimen. Now, that works in about 90% of the cases, but it doesn't work in 10% of the cases. And the 10% of the cases in which it doesn't work are the ones where the material has strong tendency to pile up, where things are very, very plastic. Then there's going to be a problem because you don't get the contact depth right. But the idea then is that if you know the depth along which contact is made, then you can get the area of contact by knowing the precise shape of the indenter. It comes from the geometry of the indenter, the known depth. If you know the area function, as we call it, the geometry of the indenter, then we can get the area. If you know the contact area, then you know the hardness, because the hardness is the force divided by the contact area. And then through this fundamental equation of nanoindentation, then you can get the effective elastic modulus. The effective elastic modulus is Young's modulus divided by 1 minus Poisson's ratio squared. And so we always like to point out there, too, that we're not measuring Young's modulus directly. We're measuring the effective modulus. So if you want to get Young's modulus out, you've got to know what Poisson's ratio is independently. Fortunately, Poisson's ratio, at least in most metals and ceramics, is about 0.3. And so when you square it, it ends up being 0.1. And so it's not terribly, terribly important here, depending on what your level of accuracy is that you need. But I do need to point out, we don't measure modulus directly, we measure effective modulus. It's a combination of Young's modulus and Poisson's ratio. Okay, how well does that work?
So the area A, should it change if you change the Pmax?
Yeah, the area will change if you change Pmax, but if you're using a geometrically self-similar indenter, and the processes are geometrically self-similar, then it's doing it in a geometrically self-similar way.
So is H a constant depending on the depth?
Hardness?
Yeah.
Yeah, that's the, boy, you're just setting me up perfectly today. So next slide, okay? So we'll go to the next slide, and that's probably going to be a good place for me to stop the morning stuff. So here are some materials: sapphire hard ceramic, gold soft metal, aluminum soft metal, where we're making these measurements by that series of equations that I showed you. And this is the modulus that comes out, assuming that Poisson's ratio is 0.3, okay? And that's as a function of the depth of contact. So here's modulus, and you can see that for gold, we're getting about 80, aluminum, we're getting about 70. Those are the right numbers within 10% or so, which is about the level of accuracy that you can expect. For sapphire, the modulus is 440 or 400 or something or other, depending. It's anisotropic, so it depends on what direction you want to consider. But you're getting about the right number. But here's the hardness over here. Now notice the hardness is doing, and notice that this is a linear scale over here. This is now a log scale over here. All right? And we're putting it on a log scale so we can get the thing plotted all on one plot nicely. But notice that even on the log scale, you're seeing the hardness creeping up there. As you go to smaller depths, you're getting the material appears to be harder. As you go into gold, same thing. And even a little bit in sapphire. As you go to smaller and smaller depths, the hardness is going up and up and up and up, which points to something that people have known for years, which is that hardness is not a good material parameter. In this case, you can see quite nicely that this hardness, if you believe those numbers, the hardness is increasing at small depths. That's something called the indentation size effect. And that's something that when nanoindentation came in the late 80s, early 90s, people started seeing these things and they started asking what's causing that. And so there's a whole wealth of literature out there right now which is on the nature of that. And it gets back to this thing that I inferred a little bit earlier, or implied a little earlier, which is as you get smaller, the number of defects that are present in that material starts to change in a significant way and can change properties. So that's probably a good place to stop. Tomorrow, I know there's going to be a lot of interest in this audience in storage and loss modulus. So maybe tomorrow I'll start from there and pick up with that in a few examples of some stuff that I've done in what I call soft materials, which are not really very soft. Yeah.
Thank you very much.
We have one question.
Okay, but, okay.
One of the things I noticed is that depending on the condition of your tip, you can get very different values for hardness.
Yep.
Can you explain why that is?
Yeah, so that's a very good point. So all the data that I showed you here this morning is done not nominally with a sharp Berkovich tip. And tips, even like Berkovich tips, you use them a few times, they start getting dull. And the tip geometry starts to change. When the tip starts to get rounded, then the contact mechanics at small depths are changing from perfectly sharp elastic plastic contact towards the contact mechanics of spherical indentation, which starts off with finite stresses and elastic deformation only. So if you've got a dulled tip, and this is something that a lot of folks don't appreciate, if you've got a dulled tip, then there is a change in the basic contact mechanics as you go from large depth to small depths that if you don't account for properly will have the appearance of making it look like the material properties are changing. Is that answering the question that you're asking? Yeah, good question.
Thank you very much.
I'd be happy to answer questions at coffee. We got to move on.